Hey, this is Professor Snell talking to Building Construction 2. In class this week, the topic of evaporative cooling came up, and I kind of tried to avoid it, just simply because it's really not what we're talking about this semester, and I didn't want to get bogged down. But it is true that it came up in what I told you to do, so I figure I should at least begin to introduce it. So here's how it came up. So we were in looking. I was saying you could look at the psychrometric chart, and so here we are in Nevada, and we've got our comfort zone over here in blue. We've got our little green dots inside of it, and then most of the dots. And the dots are all every 15 minutes of the year, I think is what it is. Are mostly out of the comfort zone. So we only have 4.5%. Looks like of our annual hours of the year that are in the comfort zone in this climate without any intervention. And so we start clicking on stuff to see what would help. Definitely sun shading of the windows helps a lot, 21%. Makes sense, right? Start clicking through the rest of these. Thermal mass isn't that much interesting. We could talk about that. So let's just click those off. Then we get to evaporative cooling, and it's giant, 35%. If we do two-stage, it's 38%. Not much difference. Let's just keep it simple. Talk about direct evaporative cooling. So what is this, and why is it of advantage to use in a climate like Las Vegas? I have to give a little bit of a sort of building physics or just simple physics lesson here, or just a reminder, perhaps it is. Let's say we have some water in a container or whatever, and it's 38 degrees Fahrenheit. If I add, let me go ahead and get fancy here. Here's our water. If I add 1 BTU of energy to that water, and again, of course, okay, so what is a BTU? BTU is how much energy it takes to raise the temperature of 1 pound of water 1 degree Fahrenheit. And it's basically the amount of energy in a match. Doesn't really matter. We're just saying that there's a certain amount of energy, very small actually, that we need to apply to this water to get it to go up 1 degree. And if I want it to go to 40, it's going to be the same thing. 1 BTU, got my water, and we're at 40 degrees. 40 degrees Fahrenheit. Now, if we get to 211 degrees Fahrenheit, and here's our water, it's going to take us 1,000 BTUs to raise this to 212, because that's going to involve a change of state. And now this is going to be water vapor. So this is a lot of energy then that it takes to go from here to here. And evaporative cooling takes advantage of that. So, and actually, by the way, so the temperature on the thermometer is called sensible heat. So that's, or dry bulb temperature. This temperature is called latent. And it's the energy in the water, in the air, in the water vapor in the air, or the liquid water. It's that change of state energy. Okay, so now let's switch to, let's say we're in Arizona, and it's 98 degrees Fahrenheit outside. Let's make it 105, whatever. Make it really hot. Degrees Fahrenheit, and 10% relative humidity. If we bring that air into the building, but through a material, so let's say this is some kind of porous filter cloth, or just, a commercial filter, Sorry, technical difficulties, that's soaked in water. What's going to happen is that air is going to turn some of that water into water vapor. The relative humidity is going to go up. Let's say it goes up to 50%. And we could look up exactly what this would be, but I'm just making an example. And the temperature then is going to drop. And that's because we are turning liquid water into water vapor, and we're taking all of this heat out of the air. This is called evaporative cooling. And yeah, you could do this by, I mean, it happens all the time at lakes, naturally. It used to be in the Middle East, they would use, ceramic pots of water, and they would induce air currents to go over them to cool. But as was pointed out in class, if you're going to lose a bunch of water in the desert to cool, maybe it's not that much of a good approach. It's going to last. That's going to make sense over time. So what we can do, and what would be the typical approach here, is just use some kind of equipment. So like this is a U.S. government little drawing of, it's just basically a fan with water being pulled across these dampened material membranes or filters, and then air is being blown into the building that's cooler and wetter. And by the way, because 10% relative humidity would be uncomfortable, so 50% relative humidity is very comfortable, and so is 75 degrees as opposed to 100 degrees. So we're improving the comfort of the air in a pretty energy efficient way. Now, the way you would probably do it in a building the size that we're talking about is with something like this. That's like a commercial unit. So this is just like a big, looks like a typical HVAC unit on a roof. It could be like a package unit that has a heat pump inside of it. We won't talk about that. That's for something later. But the point is that then you're preconditioning the air. So like here's a video, and they get into more complicated
ESC
description.
Series of semi-custom evaporative cooling units with the available two-stage
basically the air is coming in and being preconditioned. It's hot, dry air. It's being cooled, and
an indirect evaporative cooling module provides
some water vapor is being drawn into it, and so it's relative humidity
separates the ventilation airstream
increasing.
From the air solutions ESC series.
Just giving you an idea that these are commercial units that are available. And so the point is that for our purposes, when we're talking about evaporative cooling, which is true, we can get a drastic, we can get a lot of the hours of the year into the comfort zone by using evaporative cooling. But in our case, it's just going to be some kind of piece of equipment. It's not really going to change the form of the building, which is what we were talking about mainly. So definitely you can use it, but just I would suggest just saying, labeling a piece of commercial HVAC equipment on your roof as an evaporative cooler, or as a heating, cooling, ventilation unit that is preconditioned by an evaporative cooler. Now, you can see why maybe I didn't want to bring it up. That's maybe confusing to you because that's not what we're studying right now, but I thought it was a good question, and I thought it was worth trying to answer it as clearly as I could without getting into too much detail. All right. Anyway, I hope this helped.